So the beauty of matching networks based on transmissional elements is that they're incredibly simple. In fact, it only takes a couple of pieces of wire to make this thing happen. You don't need to build inductors, you don't need to build capacitors, you don't need to build anything. Just wires or transmission line sections. This particular one we're studying today is actually called the single stub matching network because it utilizes one stub only, and this can actually be either a sorted or an open stub. And it utilizes a transmission line section that actually connects the stub to the load. Now, the drawback of those matching networks is that they take space, right? See, these transmission line lengths take space, and that space is actually expensive, particularly when you're talking about an RFIC. And so you have to be careful if you don't want to dedicate too much space on your RFIC. You have to choose those lengths to be small compared to the wavelength. And so that means that those networks are useful only assuming you're operating, let's say, above 6 or 10 gigahertz, because below that, they can get quite expensive. Now, if you're building a PC board and you have the space to utilize, it's much less of a concern. But in an RFIC section, usually you will find them essentially for high-frequency applications. So let's see how those work. The idea is very simple. If you actually create a stub and you calculate the input impedance or the input admittance of an open or a sorted stub, as we have actually seen before, you will find out that they are purely reactive. In other words, if you look at the normalized Z, the normalized impedance of a sorted stub, that's what that SC stands for, it turns out that this impedance is only J tangent beta D, where essentially beta is the propagation constant for that stub and D is its length. So this is the impedance, in other words, that you're looking this way. So it's purely reactive, and the same thing is true if the stub is actually open, is also purely reactive. In that case, it basically is negative J cotangent beta D. So the interesting thing about those things is that they can basically take either positive or negative values, which means that in order for this thing to be matched, right before the stub, you need to have essentially an admittance that is plus or minus J beta. So if I can basically start with my load, I can move my load along a transmission line section with a length of L, as shown here. And I can do that such that right before my stub, I arrive with an admittance that has a real part of 1, normalized, and an imaginary part of plus minus J beta. I can cancel this plus or minus J beta with either an open or a sorted stub. And so that's the whole idea. The whole idea, which I will show with an example, is to start with a load. In this particular case, my load is 2.2 plus J.6. Move this load in a transmission line section, and we know that this happens when I actually rotate my load clockwise along essentially a circle. So move this load on this circle until I hit a load, until I hit an impedance with a real part of 1. Now that real part of 1 is actually the admittance, and so as I mentioned actually in a previous lecture, it helps a lot to utilize that circle here, the Y is equal 1 circle. This is a circle that automatically is given to you if you use the ZY Smith chart, but if you don't use the ZY Smith chart, you use the simple one I'm using here, you can actually always draw it by hand. So if you utilize that circle, you will see that very quickly there are essentially 2 points that the blue and the red circle intersect. So the first point is this guy here, the ZB1. So that ZB1 will have a real part of 0.55 of impedance and imaginary part of impedance of negative J.5. But the key is that the admittance of that point has a real part of 1. And then there is one more point, the point right here, which basically has same real part and the opposite imaginary part. So calculating essentially that length L, you have now 2 solutions. It's either going to be the length that is given by this angle or the length given by this angle. Now, as we're going to discuss later on, if that was the only design consideration that you had, clearly the length 2 beta L1 is a preferred solution to 2 beta L2 for 2 reasons. First of all, it's shorter, and so that means it's less expensive. But perhaps even more importantly than that, shorter lengths result in wideband behavior. So the shorter the length, the more wideband the behavior of the circuit will actually be. And so when you choose 2 beta L2 versus 2 beta L1, your final design will end up being more narrowband, meaning that for the design frequency it will work, but the minute you move a little bit away from the design frequency, it will deviate significantly. We'll see this in a second. But at least for the design frequency, there are essentially 2 solutions, either ZB1 or ZB2, either L1 or L2. So let's now see how things work when I choose one or the other. So let's say that I choose to work with my first point, ZB1, and either by using the ZY chart or simply by inverting this number, you will find out, as expected, that YB1 has a real part of 1, and then the imaginary part will end up being J.9. This means now I have to cancel this J.9, which means I need the stub with a imaginary part of -0.9. So I can get that either by creating a short circuit stub. So if I choose to work with a short circuit stub, I need my Y of short circuit to be -J.9, which based on the equations I just gave you before, that means that the cotangent beta D1 has to be equal to 0.9. That's essentially from the equation I just wrote before. If you do this calculation, you will find out that the solution is beta D1 is 48 degrees, or in wavelengths, D1 will be 0.13 lambda. So the complete solution for the single stub has essentially 2 lengths, and only 2 lengths. The first is the 2 beta L1, which will actually be 0.18 lambda, and D1 would be 0.13 lambda. That's one set of solutions. I could also go ahead and work with an open circuit. If I work with an open circuit stub, now my open circuit admittance has to be -J.9, which means that now my tangent beta D1 has to be -0.9, which results now in D1 to be 0.8 lambda. So the second solution now is you can still choose L1 to be 0.18, but now your D1 will be 0.8 instead of 0.13, and in degrees that's actually 318 degrees. So clearly, if you were to go ahead and work with a point B1, ideally you would like to basically choose the short circuit stub, since this would be a shorter stub, actually much shorter in this case, and a more wideband stub. I'll come back to this in a second, but let's look at the second solution. So the second solution is to pick the second point, ZB2. In that case, my 2 beta L2 will be 262 degrees, or 0.36 lambda. And similarly, I have 2 stubs that can cancel the reactive part. The first one will end up being 0.866, and the second one will be 0.117. So again, if I were to work with this solution and pick essentially the second length, L2, then the open circuit stub, in this case, will actually be preferred since it will be shorter. Now, you might say, why do you have to consider all of these solutions? Why can't you just pick the 2 shortest lengths possible? So, for example, in this case, the 2 shortest lengths possible would be this one here, 0.18, and this one here that comes from a short stub. So there are 2 answers to that. Probably the most interesting answer is that sometimes you can't actually create the stub you need. For example, here you have a short stub. If your transmission line ends up being on a substrate that is essentially it's impossible to drill, and you have chosen a microstrip line, then tough luck, you can't create a short stub. And so even though it might result in the best possible wideband solution, it may actually not work. There is also a second thing, which is actually case-by-case dependent. Sometimes you may not be able to do any sorting in a circuit simply because you will destroy your bias network. Remember that many active circuits require biasing, and that means you have to put a DC voltage, and perhaps by actually sorting your line, you might actually sort the DC bias voltage. And so sortings may not be allowed, and only open stubs might be possible. So there are application-dependent, how can I say, considerations that will actually prevent you sometimes from picking the shortest or most wideband solution, but you definitely should be able to at least identify it and try your best to make it happen.